Hi. So in the previous episode, we discussed that how to connect the continuous preference relation with a continuous utility function, right? So then we're ready to start the utility maximization problem for the consumer's theory or demand theory. Okay. So let's do this in this video. So this is the utility maximization problem. Okay. Okay, so in short, a utility maximization problem would be nothing but just a standard optimization or maximization problem, okay, and under some certain constraint, and it's nothing but this, okay. So, and we assume that the consumer has a rational, continuous, and locally non-satiated preference range, okay, and then we take this utility function to be some continuous function representing the utility or representing the preference relation, okay, satisfying all those conditions, okay. So, and then we simply narrow or simply restrict the consumption set to be the positive real numbers in L dimensions, okay. Good. So then how do we formulate or formalize the consumer's problem or the utility maximization problem? So simply we choose, so this problem is to choose the most preferred consumption bundle given some positive prices, okay, and some positive level of wealth or income, okay, so it's just the money that this person has, okay, and this is stated as follows. So the consumer's problem of choosing, okay, so the target or the variable that this consumer can choose is just this vector x, right? So choosing the most preferred consumption bundle, this x, right? And this x given positive prices, okay? So when we're using this greater sign, this simply stands for the greater relation in the vector, okay? So component-wise, each entry or each component in this vector P is strictly greater than 0, okay? So we're talking about the vectors here. And a wealth level, so this wealth level, we could regard this as income or cash or money, right? So that's how much this person has, W, which is a scalar, okay? So the consumer's problem of choosing the most preferred consumption bundle X, given the prices positive P and wealth level W to be positive, can be stated or formalized by a utility maximization problem, okay? So this is UMP in short. Okay, so this would be a maximization problem by choosing some X. Okay, so this X cannot be negative. You have to consume zero or a positive amount of some good. And the objective is this UX, this utility function. Okay, and subject to, so this P is a vector, okay, and we take the inner product with X, which is also a vector, and the total amount of money cannot exceed your budget or your wealth, okay, which is W as a scalar. Okay, so in the utility maximization problem, the consumer simply chooses a consumption bundle, okay, in some budget set, this W. Here we give this budget set a name called Warrison budget set, okay. So in UMP, the consumer chooses consumption bundle X in a rising budget set. Okay, so this we use this B to denote this budget set, okay, and put some subscripts P and W here. So this would be a set of all those X's, okay, in positive real numbers without dimensions, where we have some constraints for this X. So this would be just this budget itself. So the inner product of P and X cannot exceed this W, okay, to maximize the utility. Okay, so this is called rising budget set, okay. Good. So before we could solve this problem by adopting, for example, the Lagrangian methods or any optimization problem methods. So before we do that, we need to first establish or first to confirm that this problem, the UMP problem, has a solution at least, okay? Good. So this is the proposition 3.D.1 on the textbook. So it says that if the price is greater than 0 and the utility function is continuous, okay, then UMP problem has at least a solution. Okay, so before we show the proof of this problem, okay, so now let's take a look on the possible. Maybe we could do this later. Okay, let's first show the proof and then try to demonstrate some intuitions or some explanations behind this idea. Okay, good. So okay, so now let's try to prove this. So given that this P element wise or entry wise positive, okay, then the budget set, okay, BPW in R plus L, P inner product X less than or equal to L, W. So this budget set, it is compact, okay? So when we're saying that some set is compact and it satisfies two requirements. So the first, so we have mentioned this previously, right? So the first requirement would be bounded, okay? And the second would be closeness. So, okay, this is because it is both bounded and closed. Okay. All right. So for the first argument, that why it is bounded, okay. So this is simply because that it doesn't reach the infinity. Okay, so it is still finite. All right, and we could have certain sort of a range or limit that can still restrict the value of those x's. Okay, so that this set of x, it is contained, okay, within some range. So that is basically the intuition of the bounded. Okay, so formally or mathematically, so for any, let's say, dimension L from 1 up to capital L, okay, since we have, so each XL in each dimension, so this XL, it has to be less or equal to W over PL, okay, because we have this constraint here, right? So then we can immediately see that this XL, it is bounded by this W over PL and 0, right? Okay. For all x in BPW, okay? Thus, XL is bounded between 0 and W over PL, okay? All right. Good. So that'll be the okay, that'll be the first the first requirement for the bounded. Okay. All right, and the closeness would be trivial to show. Okay, and is obviously satisfied. So here together, we will have this the boundaries, and it is bounded and is closed, right? So and then this set of X, it will be a compact set. Okay. The budget set B is a compact set, right? Okay. So why it is important to have this set B to be a compact set? Okay. So it is because that if we have some set B to be compact, okay, then so there will be a theorem or a proposition mentioned in the appendix of the textbook saying that so a continuous function, okay, which is the utility function, it always has a maximum value on any compact set, okay. So now we have shown that this set of all those x's in this budget set is compact, okay, and then the utility function u on this x, on a compact x, and then this u always has a maximum value, okay. All right, so let's finish this argument. So then the result follows from the fact that the continuous function, which is our utility function ux, always has a maximum value on any compact set. Okay. And you could see the appendix for these for this mathematical result that we're going to build this argument on. Okay, but that is not too important in this proof since we're just using that result. Okay, good, and that is also very straightforward, right? So as long as this domain or this set X is both bounded and closed, okay, so we could simply try to reach this maximum, right? So it has this boundaries and it's limited, contained within some range, okay? Then we could reach this maximum of some some continuous function, okay? All right, good. So then with this result, then next we can focus on attention on some properties of two main objects that emerge from this UMP problem. Okay, so they're the consumer set of optimal consumption bundles. So it'll be the solution set of the UMP, and the secondly the consumer's maximal utility value. Okay, so that is the value function of the UMP. Okay, so those be the two aspects that we're going to focus on in the next stage. Okay, good. So, and later we'll introduce the those two different perspective or two different kinds of ingredients that we are looking at this problem. Okay, good.